GCC. This is our last video with Chapter 14 on intermolecular forces. We just learned about some liquid properties that are affected by intermolecular forces. So what kind of questions do we ask on this? Well, questions like these. Let's compare two liquids, propanol, C3H7OH, and benzene, C6H6. First of all, what kind of intermolecular forces do they have? Well, C3H7OH has some carbons, hydrogens, and then an O bonded to an H. What kind of force goes with an O bonded to an H? Yeah, that can be hydrogen bonding force. Okay, we have an H bonded to an O in that molecule. So the strongest force for that molecule is hydrogen bonding force. What about benzene? C6H6, and that's it, just carbons and hydrogens. So that's a hydrocarbon. What did we say earlier about hydrocarbons? They're nonpolar. So what kind of force goes with nonpolar? That's right, London force. So that's the strongest force that benzene can have, is just the London force. So propanol has hydrogen bonding forces. Hydrogen bridging is just another word for that. Whereas benzene has London force. So now let's go to our questions. Number one, which has the stronger intermolecular force? Well, London's the weakest force, so propanol. Propanol has a stronger intermolecular force. Number two, which has the lower boiling point? So if we boil easily, we're not held together very well. So that would be the benzene with the weaker London force. It's not held together very well, so it's going to boil and go into the gas state easier than the propanol. So benzene for number two. Number three, which is polar? Well, I think we already answered that question, didn't we? Benzene is C6H6. That's nonpolar. So it must be the propanol. Propanol has an OH bond, which is a polar bond, and that makes propanol polar. So number three is propanol. Which has the higher vapor pressure? Remember, if you have a lot of vapor, you're not held together very well because it's easy to pop out and go into the gas state. So which one's not held together very well? The weaker force, London force. So benzene. Benzene has a higher vapor pressure for number four. Number five, which has the lower viscosity? So low viscosity, lower force. Again, that's benzene again, benzene. Number six, which has higher surface tension, more surface tension. Higher surface tension, higher force. Which one has the higher force? The propanol. Yeah, the propanol. So there's our answers. You might want to pause here and look at these for a little bit. Good job. So that's the kind of questions you will see over this material. Moving on to the last part of this course, we're going to talk a little bit about water. There's the Lewis dot structure for water. Remember, it's bent, not linear. It's bent. We have two lone pairs on the oxygen. We have two bonds to the hydrogen. The bonds are OH, which are very polar bonds. Because the bonds are not equal and opposite each other, molecule is very polar. So H2O has a bent molecular geometry with a bond angle a little less than 109.5. We get that from our shapes table, which you should always have available for exams and quizzes, especially the final. Water has very polar OH bonds. It can dissolve some ionic compounds. According to our solubility rules, we have many different ionic compounds that will dissolve in water. Water is polar, so it mixes with other polar substances. Water's force is the hydrogen bonding force because we have an H bonded to an O. So water molecules have a pretty strong intermolecular force between them, hydrogen bonding force. Some properties of water. Again, it's very polar, which is a fairly high intermolecular force. As a result of the high force, the vapor pressure is low. When you open up water, it doesn't go psh. Because of the high force, we have unusually high boiling point and melting point for water, considering it's such a little molecule. So it's surprisingly high. The boiling point is 100 degrees Celsius. The melting point is 0 degrees Celsius. Because we have high forces, we have high surface tension. Water is weird, however. It is not a typical liquid. If you ask someone, what's a typical liquid? Most people would say water, and they're wrong. Water is weird. Water actually expands as it freezes, and that's not normal. The density of ice is less than the density of liquid water, which is really rare and odd. So ice cubes of water, ice, float in water. Most substances, when you have ice cubes, they sink in the liquid. But water's weird, and ice cubes float. So water is weird. It's not a typical liquid. So here's some of the structure of ice. We can see there's kind of big open gaps, which make it less dense than liquid water. The molecular structure of ice shows hexagons, which we can even see in the image of a snowflake viewed through a microscope. So that hexagonal pattern, again, has some empty space in the middle, and that makes ice less dense than liquid water, which again is weird. Last thing we're going to talk about is a heating curve. So we have a heating curve, it's a graph. The y-axis is temperature in degrees Celsius, starting at the bottom at 0. So that's as cold as we can theoretically get. Okay, 0 Kelvin would be as cold as we can theoretically get. So very cold at the bottom. Now the x-axis is adding heat energy to the substance. So in the corner, we have 0 Kelvin and no heat at all. So we are as cold as we can be. What state of matter will exist when we're cold? Solid, liquid, or gas? Yeah, solid. A solid exists when we're as cold as we can get. Now, as we add heat, the solid warms up. The atoms in the solid will start to vibrate a little bit more with more energy and more energy until what happens to that solid when we heat it up? Eventually it will break apart and start to melt. So the atoms are going to start to roll around each other. What state of matter do we have then? A liquid, yeah, a solid melts into a liquid. Now the flat part of that curve right there, the flat part, is where melting occurs, and it's at the melting point. Notice the MP on the y-axis, melting point. So it takes some time for all of the solid to melt to liquid, and that's the flat part. Once we have all liquid, the liquid is rolling around, and we're going to add heat and heat it up. And the liquid will roll around faster and faster and faster until eventually what will the liquid do if we heat it up enough? It'll boil, right? It'll boil into a gas. We will pull those liquid molecules apart so they have empty space in between them and it'll become a gas. So the second flat part is where boiling occurs. And if you look at the y-axis, it's at the boiling point. So we're going to turn all the liquid into gas as we boil it away during that flat part. And then we just have a gas with the atoms moving fast in straight lines, and we just keep heating the gas up theoretically forever. So this is called a heating curve. You should know all the parts of your heating curve. We have a solid sloping up, then the flat part is melting. Then we have liquid sloping up, and then we have another flat part which is boiling, and then the last part going up is gas. Here is another example of a heating curve. Just a little bit different representation, but it's the same thing. In the corner of the graph, where we're as cold as we can be, which would be negative Celsius and Fahrenheit and 0 Kelvin, we have a solid. As we add heat, we slope up that solid until we reach the melting point, and then we flatten out. Solid turns to liquid, solid turns to liquid, solid turns to liquid as we're melting, melting, melting. Once we're all melted, we start to go up again. This is when we have liquid. And the liquid goes up, 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 up until we start to boil. And then it flattens out again. Liquid turns to gas, liquid turns to gas, liquid turns to gas as we're boiling away till we've got all gas, and then it starts to go up again for gas. So that's a heating curve. Remember this graph. You need to know it for quizzes and exams. So the phase changes are the flat parts. The temperature stays constant during a phase change, melting and boiling. All the energy, all the heat energy goes into breaking the intermolecular forces, not the bonds. When we melt, we do not break bonds. We simply take the solid force and break it so we can be a liquid. And when we boil, we don't break bonds either. We have our molecules. They're in the liquid state. We pull them apart into the gas state. We're breaking forces, not bonds. So when you boil and melt and freeze and condense, sublime and deposit a substance, we're breaking or forming intermolecular forces, not bonds. I want to go backwards. If we start up here with the gas and cool it, eventually we condense and head backwards as we condense the gas to a liquid. So condensing occurs at the same temperature as boiling. Once we're all liquid, we can cool down, down, down until the liquid starts to freeze into a solid. So freezing and melting occur at the same temperature. So as we go backwards, we're freezing the liquid into the solid, and then once we're all frozen, we simply cool the solid to as cold as we can get, and we stop. So we can go backwards down the heating curve as well. All right, so remember your heating curves, and that's the end of chapter 14. I hope you stuck with me, GCC. Good luck. Bye-bye.